Professor, you're muted.
Haha. Are we there now? I am also recording. Thank you for checking. I appreciate that. I need all these reminders. So what I'm going to do is I'm going to show you about symmetric key cryptography today. And I'm going to start by teaching you some building blocks. I'm going to teach you about one-time pads, which are not a practical method, but are a good kind of beginning entry level into the topic. And then I'm going to teach you about block ciphers, which are a tool that we use to build secure encryption. And you would want to use encryption anytime you need to protect data that's like in transit for communication or in storage. So let me start with one-time pads. One-time pads are this method that are very simple to analyze theoretically. They have some drawbacks that make them not very useful practically, but that hopefully let's try to, and then we'll try to make it more practical. Okay, so we're in the symmetric key setting on protectality. So we're in the upper left quadrant for today. And the one-time pad is going to be using exclusive OR. And the exclusive OR operation, it's addition, but like clock arithmetic, modulo 2. Okay, so it is like the addition not particularly relevant for computers. And if you take something and you XOR it with 0, it stays unchanged. And if you XOR it with 1, then the bit gets flipped, it gets reversed. Okay, and it has a lot of the properties you would expect from addition, but with one weird twist. The one weird twist is that if you XOR anything with itself, you get 0. Or another way to say that is the negative of a number is itself. Like -1 is equal to 1 in this weird modulo 2 XOR style arithmetic. Okay, we're going to use this because it's very convenient for working with bits, so it's very convenient for computers. And also it's a reversible operation. Same way that like if you add 5 to a number, you can get back by subtracting 5. With XOR, if you XOR something in, you can get back by XORing in the negative, except you don't need to XOR in the negative. You can just XOR the thing itself, because like -5 and 5 are the same thing when you work with XOR. And just like we can do algebra with addition, you can do algebra with XOR. So for instance, if I have the equation that y XOR 1 equals 0, and I want to solve for y, I can do algebra to solve for y. If that was a plus sign and I had the equation y plus 1 equals 0, how would I solve for y? I would add -1 to both sides, right? So I should do the same thing, add -1 to both sides. But what is, when I work with XOR, what's the equivalent of adding -1? Yeah? Adding +1. Because +1 and -1 are the same with this modular arithmetic. Okay, so I can add 1 to both sides. And on the left-hand side, I have y plus 1 plus 1. But 1 plus 1 is 2, and 2 is 0. Mod 2, when I'm working with mod 2 arithmetic. So after I've done that, the left-hand side simplifies to just y. And the right-hand side is 0 plus 1, or is 1. So the solution to this equation is y is equal to 1. Yeah, so really this is a solution mod 2. I'm not distinguishing between 1 and 3 and 5 and 7. Yeah. But I'm really going to think of it as like the only values y could have as being either 0 or 1, because it's like a bit. And 0 is kind of like even, or 1 is like odd. Okay, so that's a little bit of math background. And then the one-time pad is going to use this XOR operation. So with a one-time pad, to encrypt a message, I write the message as bits, and I have a key. I need a key to encrypt with. I'm going to assume that both Alice and Bob know that key. They prearranged what the key is. And the special thing about one-time pads is the key needs to be the same message. The randomly chosen bits, a bunch of bits, each one chosen randomly, like by flipping a coin. We're going to assume both the sender and the recipient know this key. And to encrypt a message, we're going to line up the key and the message. They have to be the same length in bits. And then at each position, we're going to do this XOR operation. Okay, so it's like the simplest possible operation you could possibly imagine for how to encrypt. For instance, at the first position, my key is 0 and the message is 1. So what should the first bit of the ciphertext be if I'm going to obtain it by XORing 0 and 1? What do I? 1. And at the next position, I have a 1 and a 0. What should I get? 1. And a 1 and a 0, XOR those is 1. And a 0, 1, 1. So I can just kind of fill in each bit position. And I get the ciphertext like this. Okay, very simple encryption method. Question for you, is this reversible? Can the recipient, if the recipient knows the key, can they decrypt? So the recipient knows the ciphertext and they know the key. Can they figure out what the message was? I see you shaking your head, yes. Tell me why. Yeah? To send it back through XOR the C and K. If I take C and I XOR the key with C, you'll get back the message. Like, look at the first bit placement. C is 1. The key was 0. 1 plus 0. 1 XOR 0. I get back 1, and that was indeed the first message of the bit. The first message of the bit? The first bit of the message. So why does this work? Why can I get back the message by XORing in the key? I'm like, started with the message, I XORed in the key, and then I XORed in the key again. It's like I added K, and then I added K again. So I added 2K. But remember what modulo 2 arithmetic, you add in anything twice, that's the same as adding 0. So you added in K to encrypt, add in another K to decrypt. That's the same as like adding nothing in, so you end up back with the message. Okay. Good. Good. So if we're like specifying this in a formal mathematical way, we remember encryption has 3 operations: generating a key, encrypting, and decrypting. The way we'd specify this scheme is we would say generating a key you do by picking a random bit string. Each bit is 50-50 uniformly at random, 0 or 1, independent of all the other bit positions. The key in a message is you XOR them. When I write K XOR M, these are long bit strings. I'm going to assume that each bit position is independently do an XOR. There's no like carry bits or anything. And then the way you decrypt a ciphertext C is you XOR the key and the ciphertext. To check correctness, we have to check that if you decrypt an encrypted message, you get back what you started with, and you could work through the math, and you'll see that when you decrypt an encrypted message, the ciphertext is K plus M. Decrypting that, I add in K again. So I get K XOR M. And if you work through those rules of algebra we previously had, K XOR K is always 0, regardless of what K is. So this is like 0 XOR M, which is like M. So you can kind of do this kind of an algebraic derivation and verify that decryption will undo encryption. So the first thing we want any encryption scheme to be is correct. Decryption undoes encryption. We're good there. The next thing we want is security, that it preserves the secrecy of the message, that an attacker who observes text can't learn anything about the message. Okay, so we had this like formal definition of a way to define what it means for an encryption scheme to protect confidentiality, this NCPA business. Let's look at a simplified version of that definition. In the full definition, the attacker could like specify some messages to be encrypted. This is the chosen thing. But let's ignore that part. And focus who just can observe the ciphertext and wants to try to infer some partial information about the message. Okay, so in the simplified security game, the attacker, the Eve, we're going to allow Eve to pick two messages, to constrain Alice to send only one of two messages. Okay, so this is like now thinking about security, even in the worst case, where Eve already knows that Alice is sending one of two messages. And actually, Eve can even pick which two those are that'll be like as different as possible or make it as easy as possible for Eve to somehow break the encryption. So in this game, Eve picks two messages for Alice to choose. Alice then encrypts one of those messages without telling Eve which one she's encrypted. And Eve has to guess which message was encrypted by looking at the ciphertext, the result of the encryption. And of course, Eve doesn't know the key, so Eve can't directly decrypt. So let's look at this security game and figure out whether or not Eve can gain any information about the message from the ciphertext. Or in other words, like whether Eve can win this game, can guess which of two messages was encrypted based on the ciphertext. Okay? Yeah.
Eve doesn't know Alice if she compared.
Eve does not know whether Alice picked the first message or the second message. That's what Eve's going to try to figure out. So like one message might be buy stocks and one might be sell stocks. Or one might be no. Does Eve know the encryption algorithm that's being used, the scheme that's being used, like that it's XOR? Yes. So remember we talked about Kirchhoff's law or no security through obscurity. So the assumption that we're going to analyze all of our schemes under is that Eve, the attacker, knows the full algorithm we're using, knows everything about how we're doing the encryption, except just doesn't know the key. That's the one thing that Eve doesn't know. Okay, so Eve knows we're using a one-time pad with this XOR, so on and so forth. Just doesn't know K. Yeah, do you have a question or comment? No, okay, good. Okay, so this is like the mathematical definition or the way we're going to probe whether or not Eve can learn any partial information about the message from the ciphertext. Questions about the setup? Okay, let's check what you think. Who do you think wins this game? Do you think Eve can win this game and predict which message was encrypted with better than 50% chance? Or do you think Alice wins this game? Eve can't do any better than just random guessing about which message was encrypted. What do you think? Okay, so your intuition is for short messages, Eve can gain some information, but for long messages, Eve is screwed. Okay, what are you thinking? Okay, so you're thinking if Eve can XOR both of these messages, she can learn something. So Eve should be able to win. In this setup, Eve sees one ciphertext, the encryption of one of these messages, not both. Eve doesn't have the key, and Alice is picking one of these two messages and encrypting it, and Eve sees the resulting ciphertext but doesn't know which of the. Yeah. Okay. What's your intuition?
the result could be also like each bit is.
Okay, so your intuition is that Alice wins this game. Eve can't do better than random, because if the key is chosen randomly, then the ciphertext is random, and so Eve's not getting any information from it. What are you thinking? Oh yeah, from any mess, depending on the key, you could reach any ciphertext. I like that. So another way to say that would be when Eve observes a ciphertext, there is a key that means it could be M0, and there's also a key that means it could be M1. Both of those are possible, or like there's a way to make that kind of consistent. So Eve can't rule out M0 as impossible, and Eve can't rule out M1 as impossible. I like that observation. Eve can't rule them out, but what about maybe gaining some partial probabilistic information? Could she maybe come up with some way that so she can guess, I think it's 2/3 likely to be M0 and 1/3 likely to be M1? What are you thinking?
Also, like,
Maybe the structure of the message could give her some hints. Yeah, that's worth worrying about. What are you thinking?
And string also you string all ones. C50. String with zeros really. Maybe half or 0.
That would be a for Eve to try. She could try sending one message is all zeros, M0 is all zeros, and M1 is all ones. One of those gets encrypted, and then maybe Eve might try guessing if there's more ones than zeros in the ciphertext, guess the message was ones. And if there are more zeros than ones in the ciphertext, guess the message was zeros. Do you think that'll work?
I think it depends whether or not they reuse the same one-time pad, like the part of the key.
We're going to assume the one-time pad, the key is not reused. It's only used for a single message. There's no reuse. This key gets used for one message and then thrown away. Yeah?
I don't think it works.
Don't think it works. Why not?
Because 0x for 1 is 1, 0 is 0, so it's still keep it.
Yeah, so the key is like 50-50 likely to be 0 or 1. And if it's a 1, it's going to flip. Yeah, so it doesn't work because like you're equally likely to stay the same as the message or to flip to the reverse of the message. Yeah?
I'll say like you can have like M0 being like a string of all zeros, except you choose like one bit to specifically be 1, and you kind of do the same for like M1, but like there's a different bit but it's like all zeros, and you choose a different bit that's it.
Oh, they're both all zeros except M0 is 1 in the first position and M1 is 1 in the last position, maybe.
Something like that.
And then what would you use based on the ciphertext? How would you guess which of those two messages was encrypted?
I guess just by knowing like you pretty much apply like the XOR on it,
Yeah.
and you're able to like I don't know how to explain.
Yeah, I don't, it's not, yeah, okay. So you've got an intuition there might be, try these special pair of messages and maybe something could leak. Yeah, I can see where you're coming from. Yeah, what are you thinking?
That situation, because even if you're just looking at those first 2 bits, you still have a 50-50 shot of guessing whether it was flipped from 0 or flipped from the 1.
Like,
Yeah, it's hard to explain, but it feels like even that strategy won't work. Maybe something we could try. This is mysterious. It's kind of hard to tell whether or not this should be secure or not. It got like reasons suspicious and all reasons to think maybe it's secure. And maybe we should care. Like this has actually been used for communicating with spies, and maybe we should try to figure out whether it's secure. Maybe a thing that would help us would be to start with a special case. It's hard to think about, so maybe we can start with a special case of a 1-bit message. So let's suppose that M0 is just the 1-bit message 0, the 0 bit, a single 0 bit. And the other message, M1, is a single message 1, a single 1 bit. And let's try to figure out, for that pair of messages, whether or not the ciphertext can help Eve guess which message was encrypted. So the key is going to be a single bit. All. Suppose that Eve observes the ciphertext is 0. Okay. What are the chances? What are the chances that Alice encrypted the 0 message? (50-50). Why 50-50? Yeah.
One, 0. So 1 will give you a 1, give you 0, depending on.
The keys are equally likely. So one key will give you a 0 and one key will give you a 1. Yeah, so if we observe a 0 ciphertext, that could be a 0 message if the key was 0, or it could be a 1 message if the key was 1. Both keys are equally likely. So if you observe a 0 ciphertext, both messages are equally likely. So Eve can't actually guess better than 50-50 which of the two messages was encrypted. She can't do better than 50-50 for a 1-bit message. Let me check how we're doing on this so far before we get into anything more advanced. Yeah. Don't worry about n-1 yet. I want to check if we're all good with 1-bit. Then I'm going to come back to you. I promise. I'll come back to you. Questions about what's going on with 1-bit? Yeah?
You also have to send the key. So like.
You're worried about how the recipient knows the key. Yeah, the recipient needs to know the key to decrypt. It's kind of a problem. We're going to assume, remember I said we're a symmetric key world? Last lecture I said we were talking about symmetric key cryptography. I'm going to assume somehow Alice and Bob have arranged in advance for a key. And they both know the key and no one else knows it. And like I said last time, that's not a very realistic assumption. So like, it feels funny spending so much time talking about this scenario that's not very realistic. But it's going to be realistic. We're going to have a way to solve that problem. So I just ask for your trust for like another lecture that there is a way, there actually are realistic ways to arrange for Alice and Bob to know a key that no one else knows. Now I'm like having you imagine they got together in a coffee shop and they like wrote down the key and like, oh my gosh, that's crazy. But yeah. Would this still work if M0 and M1 were the same thing? Wouldn't this only work if they're the same length? Yes. Say more about why. Yeah, totally. Oh, I like it. You are thinking like a cryptographer. You're thinking about the things that could go wrong. The length of the ciphertext is the same as the length of the message. So by observing the ciphertext, Eve learns how long the message is. So if M0 and M1 were two different lengths, Eve could tell which one of them. Yes, you're absolutely right. So this is not an issue that comes up with 1-bit messages. We're going to see in a moment if you want to focus on longer messages, we need to restrict to the case where M0 and M1 are the same length. Otherwise, Eve can win. Another way of saying it is, the scheme does reveal some partial information about the message. It reveals the length of the message. We're trying to figure out if it reveals anything more than that. You're absolutely right. Okay, are we good? Are we good with the security of this for 1-bit messages? If not, I want to kind of try to resolve that first before we go into other questions. We're good. Okay. All right. So now what I'm going to ask us to see is if we can generalize to n-bit messages. We're convinced this is secure for 1-bit messages, but is it secure for n-bit messages? You had a question.
I wish you this type that n-1 bits are 50-50. I think that's pretty. Yeah, probably.
Use induction. That seems plausible. If like n-1 bits are secure, and then that last 1 bit is also secure, and so it should be secure with n bits too. What about 2 bits? We could start with 2. We could like, maybe that's easier. I like small numbers. 2. Do you think it's secure with 2 bits? Does anyone want to give me a reason why it is? Yeah, give it a try. Yeah,
Then
yeah, 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 yeah. It feels like the bit positions are separate and the keys, for each bit position is chosen independently. So because each bit position is secure, they should, like as a whole, it should be secure. Another way to do that argument, if that doesn't sound convincing, is for a 2-bit message. If I observe a ciphertext, there's a single key that would make that ciphertext consistent with M0. What's the value of that key? If the ciphertext is C, what key would decrypt C back to M0? Yeah? M0 XOR C. If K equals M0 XOR C, then decrypting C gives you back M0. And that's the only key. And if I had the ciphertext C and I wanted to decrypt to M1, there's one key that will do that. M1 XOR C. So if I have a ciphertext C, there's one key that goes back to M0 and one key that goes back to M1. And both of those keys are equally likely to have happened. Because out of all the 2 to the n possible keys, we're choosing uniformly at random among all 2 to the n possible keys. So every key, each of those 2 to the n possibilities for the key has the same probability of occurring, 1 over 2 to the n. So the probability that the key is M0 XOR C is 1 over 2 to the n, and the probability that the key is M1 XOR C, 1 over 2 to the n. So we actually just proved this is secure for any length message. Okay, so this is secure, and Alice wins the game. Eve can't do better than 50% than just blindly guessing. So that means that Eve is not learning any information about the message that was encrypted, not even partial information, not even like, was this in English or French, or, is this, I don't know, is this generally positive or generally negative? There's no partial information that Eve can learn. Okay, so if you want to look through the slides, you can see kind of like a mathematical proof of this, but I've kind of sketched it for you already. One possibility is that the key was C XOR M0, and the other possibility is that the key was C XOR M1. And both of those keys are equally likely. Both of these possibilities are equally likely. And so Alice, the best that Alice can do at guessing which of these 2 possibilities we're in is they're both equally likely 50-50. All right, so the one-time pad is secure as long as you follow all these restrictions we set up. Like a key gets used only once, and the message that we're okay with revealing the length of the message that was encrypted. So in some sense, this is the first piece of good news we have. And this was invented in, I think, the 1940s. So you are now modern on cryptography up to the 1940s, that it is possible to encrypt securely, and we can even come up with a scheme where we can have a mathematical proof that it's secure. So this is the first piece of good news. What we're trying for, there's at least one way to do it, even if it's not very practical. But now I want to warn you about some of the practical dangers of using the one-time pad. You might be thinking, okay, great, we got a solution. I've got a mathematical proof that it's secure. Let's use it for everything. But it does have some weaknesses. And one weakness is, what if Alice sent a message to Bob, and now she wants to send a second message. She's like, well, I've got a key. Let me use that same key to encrypt a second message. What if we use this one-time pad scheme to encrypt 2 different messages with the same key? Is that secure? And I see people shaking your heads saying no, and you've got a really good intuition. Intuition for why that sounds like a dodgy thing to do? Yeah? What would happen if you XORed those 2 ciphertexts? So the ciphertext when encrypting the first message is K XOR the first message, and the ciphertext when encrypting the second XOR the second message. If I were to XOR those two ciphertexts, we would get K XOR first message, XOR K XOR second message. But like, addition and XOR, you can reorder those in any order you want. So there's going to be a term in there that's K XOR K. And what is K XOR K? It's 0. And so when you XOR those two ciphertexts, what's going to drop out is the first message XOR the second message. That doesn't necessarily reveal either message in its entirety, but it gives me some information about the relationship between the two messages. In particular, it tells me what bit positions they agree and what bit positions they differ. Okay, so if we use time pad twice, Eve can see these two ciphertexts, and from this she can learn partial information. By XORing these two ciphertexts, she can learn partial information. She can learn information about the exclusive OR of the two messages. And for an encryption scheme, that's considered bad. We don't want to leak even partial information. We want to leak nothing. If we're leaking anything at all to the attacker, to the eavesdropper, then we consider that no good. I'm not satisfied. I demand more. Okay, so from a cryptographer's perspective, we would already say this scheme is no good if you're using it to encrypt two messages. Unsatisfactory. Go back to the drawing board. Yeah. Does the eavesdropper know that the key is being reused? Good point. Yeah, let's assume the eavesdropper knows. Maybe it's like written down somewhere that you can use the key multiple times, or the only thing that should be secret, the only thing we want to rely on for security is the secrecy of the key. We don't want to rely on anything else. So we don't want to rely on Eve like not realizing that the key was used twice. We're making this kind of very conservative analysis assumptions, the worst case. Okay, so one-time pads are not secure if the key is reused. And actually, it's even worse than that. It's really bad. This is a kind of a fun puzzle you could do sometime on your own if you wanted. If like both messages are like ASCII text and you learn the XOR of both messages, a lot of times it's actually possible. It's like one of those like, puzzle kind of things like you might find in the back of a newspaper, except a little different. But it's actually possible to recover most of both messages. It's kind of surprising, but there's enough redundancy in like English text. To give you some like hint of an intuition, why that might be so. In English text, each letter has only maybe 1 or 2 bits of entropy. If you've seen a whole long text and you need to predict what the next letter is, you can often guess right what the next letter will be, like 50% of the time or 25% of the time. So each 8-bit chunk, M0 only has a couple of possibilities probably, and M1 probably only has a couple of possibilities. So if you already know the beginning of M0 and the beginning of M1, there's not that many possibilities for what the next byte of M0 would be and what the next byte of M1 would be. And you check all those possible XORs and see which matches the actual observed XOR, and you can often figure out what the next byte of both messages would be. That's not important. You don't need to know that for this class. But it's not just a theoretical weakness, it turns out. It's like really bad in practice. If you use a one-time pad and you encrypt 2 messages with the same key, often an eavesdropper can recover a lot of both messages.
So, pointing out like that, so assuming in the real world, it's definitely more of a balance of just because something's secure doesn't mean it's kind of like user friendly in this new way. Like they would have to switch keys every time.
This is so not user friendly.
Even switching keys is.
Switching keys is ridiculous. It's bad enough that I have to sit down in a coffee shop, like Alice and Bob have to sit down in a coffee shop beforehand and agree on a key. But now they have to agree on a whole bunch of keys, like for as many messages they'll ever want to send to each other. Yeah. So you're absolutely right. The one-time pad is really nice because it's a little bit of good news that it's possible to achieve secure encryption, but it's super not useful in practice because it's not practical to pre-exchange all that key material, usually. Yeah,
So if you're sending like a one-time message, would a one-time pad be secure then?
yeah. Yep. OTP? OTP, what it stands for one-time pad? Yeah. Yeah. Okay. I want to just kind of a side note. We talked about the stronger notion of security in CPA, security against chosen plaintext attack, which incorporated both that Eve should not be able to gain any partial information, and also that Eve should be able to submit some chosen plaintext, some messages, and get Alice to encrypt those. And that shouldn't help Eve decrypt other messages. With the one-time pad, for kind of a boring, stupid reason, the one-time pad does not meet this security definition. Because this security definition involves using the key multiple times, and the one-time pad is not secure if you use the key multiple times. So if Eve says, first, I want you to encrypt the all zeros message, and she gets to see the encryption, she learns the key. And then now if she says, okay, Alice, go encrypt whatever message you want, Eve now knows the key and she can decrypt the second message. So the one-time pad is not secure in this stronger sense that I kind of laid out earlier. So the one-time pad is just not practical for a bunch of reasons. One is you need a bunch of keys. The second reason is we need to get those keys to everybody, which is like not reasonable. But there is one neat thing about the one-time pad, which is it doesn't require computers to calculate. You can do this by hand. This like XOR operation you can do by hand. So it's very simple. For that reason, the one-time pad has been used by spies to communicate securely back to their home country. Before the spy embeds into foreign territory, they get given a key material, pads, like a bunch of pieces of paper with the keys written on them. That's why it's called a pad, because it's like a pad of paper with key material written on it. And then each time the spy wants to send a message back home, they pick a new piece of paper and they encrypt their message with that piece of paper, and then they like get rid of that piece of paper and they don't use it again. The Soviet Union used this for a while with encryption with their spies abroad. And a way that this gets used, as far as I know, maybe still today, it's really hard to tell, but best guess is it might still be used today. When the home country letters wants to send a message to one of their spies, what they do is they send a message over the radio, over shortwave radio, and their spy they've prearranged with their spy, listen for messages at a set time each day, get out your shortwave radio and listen for messages. And you can go find these shortwave radio stations that are known as number stations. And at a certain time, like exactly on the hour, each day, what you hear on the station is an artificial voice reading out a sequence of digits. 0, 7, 3, 9er, 2, 7, and it just goes on for that like 5 minutes. And our best going on with those stations is spy agencies communicating a message to their spies. So those are ciphertexts being transmitted over the radio, and the spy is then getting out their shortwave radio, decrypting with the key material that was issued to them. Famously, the Soviet Union used this approach for communicating with their spies, and it was discovered, the US discovered somehow, I don't know how they figured it out, but they discovered that the Soviets were reusing key material multiple times. I think they like analyzed the ciphertext and they saw some similarity between the ciphertext, and they were able to like deduce that they were doing a one-time pad but reusing the key multiple times. And I think what later was going on was this was in the 1940s. The Soviets, the way they generated keys was they had people like sitting in a factory somewhere, like rolling dice or something and writing down the numbers to come up with the key material. Super tedious, like thousands and thousands of these numbers. And it was so tedious, they started and random numbers and then write them down multiple times. So they ended up with the same key being used for multiple messages. And there was a major effort by the US who were able to use that fact to decrypt a whole bunch of messages, communications between Soviet spies and back home, and like roll up a bunch of spy rings and like observe what they were sending back. Super secret stuff that wasn't declassified until 1995. So like for 50 years. I guess this was getting exploited for maybe 20, 30 years and kept secret for another 15 years after that. So one lesson here is like you were bringing up human factors. Encryption algorithm that is secure like mathematically or looks good on paper can totally fall apart if the human factors are bad, and the human factors were really bad. This is a very fragile system. All right, so one-time pads, secure in theory, very simple and easy to analyze, not very useful in practice. Question?
Like, just like not without like ever, or is it like it's only like intentionally? So it feels like we like think like that. Like you're like into the n minus one possible for the next.
Aha, I see what you're saying. You're saying if I never can reuse a key, do I have to make sure that the second key that I pick is different from the first key? As I use more keys, I'll have fewer and fewer options available to me. Okay, so the formal mathematical requirement, every message, you have a separately chosen key that was chosen random, independent of all the other keys. So if I pick one key and I reuse it for two messages, I'm violating the mathematical assumption. Warranty is voided. The warranty said, pick a key for the first message randomly. The second key for the second message also picked randomly, independently of the first key. If it's not independent, then you know you have no guarantees.
Second key doesn't count.
That's okay. When you pick the second key, you don't need to remember what the first one is and make sure it's different. You just need to make it random and independent of the first one. Yeah. Yeah.
The message is actually a list of future keys. So then every single time every single time you get a new message, you just move down that list. And then you use that key for the next message, and then you toss it out, and then you use the next key, and so forth.
That totally works if Alice and Bob have pre-agreed on a list of keys. That's exactly what you should do. Alice has 100 keys. Bob has the same 100 keys. Each time they use one, they cross it off and they throw it away. You might be tempted. I'm not sure if that's what you were proposing. The other thing you might be tempted to try is say they only need one key. And then when Alice wants to send one message, she picks a second key. She appends that to her message, and she encrypts the combination of her message and the second key. And now they both know a second key they can use for the next one.
Yeah.
What's wrong or something, you know, what's dodgy about that scheme I just proposed?
Bob doesn't know.
Bob doesn't know the key, but he can decrypt the ciphertext. So now he knows. Yeah, like the first 100 bits is the message, and the next 100 bits is the second key to use. Did you have your hand raised? Yeah. Don't have enough bits in your key. What do you think?
It would be possible to know the length of the second message, then you just take the end that many bits first message, or that many bits somewhere within the first message, and just keep comparing until you find a like normal piece of English text deciphered out of that. Because then you would have some form of the key encrypted. Without
I'm getting a little lost. Are you worried about security?
Yeah.
I think your scheme would be secure if we're how we did it. Yeah.
Well, since the key needs to be the same length as the message, if you add a key to the end of the message, then
The second message you send can only be as long as, like, the key, the extra bits that you have.
Yeah, we're gonna have a problem with length. We're gonna have a problem with the length. So if I know that I'm gonna want to send 10 messages, each 100 bits long, one thing I could do is I could just arrange in advance 1,000 bits of key material, 10 100-bit keys. You're trying to avoid that. But if I want to use your scheme, then like, yeah, I'm gonna run out. I'm gonna run out of bits. Sorry, go ahead.
I think you just use the key, like if you have like an extra like module or whatever left over of the message, you just use the first few bits of the key to decrypt that, so then you can use any, like.
You can't use any part of the key to encrypt both a message and another key. That would be a 2-time pad.
I mean, like if your key was 5 bits and your message is like 8.
Yeah.
Use the key for the first 5 bits and then just use the first 3 bits of the key for the next 2 bits. Is that okay?
If I have a 200-bit key, one thing I could do is I could send a 200-bit message and then it's done. I've used up my key material. Another thing I could do is I could send a 100-bit message and then use the other 100 bits of my key to encrypt a new key. But the new key will be only 100 bits. So I can use that new key to only send another 100 bits of message. So in the end, I still was only able to encrypt 200 bits of messages. So it's like there's no free lunch here. If you have 200 bits of key pre-exchanged, you're only going to be able to send Alice and Bob can only send 2 bits of messages between them, and then they run out of key. Yeah. Okay, don't worry about it. If I lost you, don't worry about it. We were exploring something to try to get around this length limitation, but it doesn't work. I think this is a great time to take a break. Let's take a 5-minute break. See you in 5 minutes.
I think stop and.
Thanks for message, then I keep. So can't you just make it? I think it's a good time to reconvene. Thank you for your patience with me in such a long lecture. So what I want to talk about next is a tool you can use to build a better encryption algorithm that will solve many of the issues with the one-time pad. And I want to show you the concept of a block cipher. And a block cipher is a building block you can use to build a better encryption algorithm. And we're going to use the block cipher as a building block to using once we have a block cipher, then we're going to use this mode of operation to get an encryption algorithm. So block cipher is a building block that can encrypt short messages, and the mode of operation lets you extend that to encrypt any length message you want. So what is a block cipher? A block cipher is an algorithm you can use to encrypt a 128-bit message. That's what a block cipher is, basically. That's the intuition. I'm playing a little fast and loose. By being a little more precise, what it is it is a permutation. And by permutation, I mean a bijective function on 128-bit strings. It doesn't have to be 128, but 128 is a common number used. So what that means is, what's a bijective function? Yeah.
Think the domain is something in the range and go back to one.
Yeah, a function where you can go both forward and backward. Takes everything in the domain to something in the range, and everything in the range to something in the domain. Another way to say it is it's both surjective and injective, or it's both one-to-one and onto, or it's a reversible function. Okay. So what that means is if you were to imagine writing down all the 128 bit strings of length 128, how many of those are there? 2 to the power 128, a lot. If you were to write all those down, that's the domain, and write all those down, that's the range, then there'd be some crazy mapping that's mapping each one in the domain to one in the range. Like this picture shown down here, except I can't draw 2 to the 128 values, so I've done for a 2-bit strings. This would be an example of a bijective function on strings. And the reason we want bijective, by the way, it's kind of intuitive. We want to be able to decrypt. We want to be able to undo this operation. So it'd be bad if 2 inputs gave the same output, if 2 messages encrypted to the same ciphertext. So as long as it's bijective, that'll never happen. Okay. So we're going to have this, I'm going to call it a permutation. But when I say permutation, you're going to know I mean a bijective function or like a reversible mapping. And permutation, just to be clear, it doesn't mean that the bits of the input got, like you notice 1, 1 here maps to 1, 0. That's not a reordering of the bits. It's a reordering of 2-bit strings. Okay, so I just hope I don't get you confused with this word permutation. But so far I haven't said anything about a key. So where does the key comes in? The place the key comes in is that each key implicitly defines another one of these permutations. Okay. So for a particular key, particular mapping, but for a different key, you get a different map. Okay, so a block cipher has this ability to encode, ability to decode, and the encode takes as input a plain text to length of 1 block, typically 128 bits. And it takes as input a key, and it outputs a ciphertext that is 1 block long, typically 128 bits, same length as the input. And usually that length is fixed, like it has to be 128 bits. If you want 129 or 127, too bad, not supported. 128 or nothing, baby. And then the decode operation is just the reverse that undoes the encode operation. So that's what a block cipher is. And a block cipher is an algorithm that describes how to compute these two functions. And what properties we want from that algorithm is that the encode operation for any particular key, if you focus on a particular key, then the mapping from plain text to ciphertext needs to be a permutation so that it can be reversed, and that the decode operation is the inverse, is the undoing. So that's correctness. That ensures that when you decrypt, you get back what you started with. Also, both of these operations should be very fast because we want to be able to encrypt stuff very fast. And then finally, security requirement. I'm going to have to say a little bit more in a moment what security requirement is. But basically, like that it scrambles up the bits real good. It doesn't leave any patterns behind. So let me say a little bit about what the security requirement is. Security requirement is that it's kind of like, imagine that the designer of this scheme, for each possible key, chose a permutation and chose that permutation randomly. Among all the possible permutations, randomly chose one. There's a huge number of permutations. It's like 2 to the power 128, but that factorial. So crazy number, chose one at random. And then for the next key, possible key, chose another one uniformly at random, and so on. For each key, randomly chooses one. And then uses those permutations as the encode and the decode operation. It's not actually how block ciphers are defined, but what we want is something as good as if you did that. If you did that, that would be good from a security perspective. And we want something that's like as good as that. So the actual security requirement is that just by running the algorithm and looking at the inputs and the outputs, you can't find any patterns that would let you tell that what the block cipher designer did is any different from this, like choosing permutations randomly. It's if each key corresponded to a different random permutation. And if you want some intuition for what it means to choose a permutation randomly, it's like you first choose where 0 maps to by uniformly picking at random among all these 4 possibilities. And then you choose where 1 maps to, well, it can't map to the same thing 0 did. So one of those possibilities is crossed out. Now there's only 3 possibilities. So for 0, 1, you choose randomly, uniformly at random among the 3 remaining possibilities. And then for this next input, 1, 0, now there's only 2 possibilities it could map to. So you choose uniformly at random which of those 2 it maps to. And this 1, 1 then is going to be forced about where it maps to. So we imagine like an ideal world where that's how a block cipher worked, just by that random thing. But then the real world, the block cipher is actually some fixed algorithm that doesn't have any randomness at all. It's actually deterministic. And the security requirement is that if I either gave you a real block cipher with a randomly chosen key, so you can do encode and decode operations with that key, or I gave you one of these randomly chosen permutations, like the ideal thing, and you get to do interact with that as many times you want, send as many inputs in as you get, see what the outputs are. You can't tell which of those 2 types of systems you're interacting with. You can't even get it's better than 50. Like there's no patterns that are preserved. See, the good thing about random permutations is they like conceal all patterns about the input. They're not revealing anything. Like there's no pattern that's retained, like the XOR of the input bits matches the XOR of the output bits or anything like that. No, that's not going to happen for random permutation. So if you have a block cipher that satisfies this criterion, no, that won't happen for the real block cipher either. So this is like this formalistic, mathematical definition of what constitutes a secure block cipher. And the end result is that there are no correlations between the input and output that are, usefully detectable. I just dumped a lot of math theory on you. So you can totally stop me now if you want. Or I can keep going. Okay. Yeah.
The function one set, the power set, zero one, this, this data to the, where it's sort of all that, the power.
Yes, you can think about it that way. The encode operation, this E, is a mapping from the set of all possible keys to the set of all permutations on 128-bit strings. And doesn't matter. Okay. I know this is like pretty, I don't know, this is an arcane way to describe what it means to be secure. But the reason the cryptographers use this is because it has a precise mathematical definition that we can like reason about and prove theorems about. Okay. So how might someone try to attack a block cipher? One is known plain text attack. Let's suppose that we have some message that was encrypted with a block cipher, and we know what the message was and what the corresponding ciphertext was, and we want to recover the key because the same key was used for other messages. We're going to be able to use this key for encrypting many messages. Then the most natural, simplest possible attack you could imagine is an attacker could try all possible keys, try encrypting the known plain text, and see if what you get out matches the known ciphertext. And if it does, then probably you got the right key. That's called a brute force attack. Try all keys. Look for a key that appears right, appears consistent with what you know. With modern block ciphers, this is completely infeasible. For instance, a modern block cipher might have a key that is 128 bits long. So how many possible keys do you have to try? You have to try all 2 to the power 128 possible keys if you want to do this brute force attack. And how long will that take? Well, I showed on this slide, like under some very generous assumptions about having super powerful computers, it would still take 30 trillion years, which is like longer than the expected lifetime of the solar system. So not feasible. Not feasible to do brute force attack. And if you feel at all uncomfortable, you can actually use a 256-bit key. Many modern block ciphers support a 256-bit key. And now you can do the same calculation. You'll find it's even more ridiculously impossible. Exponentials are like numbers with exponentials grow so fast that it's completely impossible, completely inconceivable that anyone could possibly do a brute force attack against a 256-bit key. So basically, we don't have to worry about brute force attacks.
Is there some computers that could do 128?
Why 256 and not 128? There's really not a good reason. Cryptographers tend to be really conservative. They've seen so many of these horror stories where they were sure that a scheme was secure and then it turned out someone found a vulnerability in it. So they like to put a safety margin in there. And so like, we're sure that 128 is enough, but let's just double that just in case. That's basically the reason. And the other reason is because it doesn't slow it down very much, because we can. So why not? If it's almost free. And modern block ciphers are very, very efficient. They're very efficient. They use a bunch of operations like XOR and addition and memory lookups. And you can easily encrypt many gigabytes per second. You can encrypt faster than you can send stuff over the network, even if you have like, fiber optic network. So they're very fast. Symmetric key block ciphers are very efficient, which is awesome. And the dominant standard right now is one called AES. That's one that was, is basically everyone uses AES today. There are other alternatives, but it's the most widely used. And it's believed to be very secure. It was designed like 25, 30 years ago when the US National Institute of Standards Technology said, we need a secure block cipher, came to academia and industry and said, come up with your best designs and submit it to this competition, and we'll pick the best one. So they ran this long 3-year process where everybody in the world who studied this field tried to come up with their best design of a block cipher, submitted it. There were 15 submissions. Then everyone tried for several years their hardest to find any security weaknesses in any of them, even theoretical. Close to 10 of them got knocked out. I think 10 of them got knocked out either because someone found a very theoretical security weakness in them, or they were really slow. They came down to 5. They studied those a whole bunch more, and finally chose one that was like the best. It was the fastest. It was like very, you know, as far as we can tell, super secure. We have no idea how anyone could possibly attack this block cipher. And we ended up with one called Randall, and now it's called AES because it was chosen as a standard. So this is the standard that everyone uses. And I was super fun. I got to be on one of the teams that was like designing one of these and like trying to attack the other block ciphers that other teams came up with, and like really like fun energy to be in the field at the time. Yeah. Twofish was not from Berkeley. I wasn't at Berkeley at the time. Yep. Well, I guess I was at Berkeley at the time, but it was led by a team by this independent consultant. Yeah. Yep. 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 Yes, they are. So they're going to solve this problem of the one-time pad. One-time pad, you can only use a key for one message. These things, you can use them for multiple messages. Yeah.
Why is it called two?
Ours was used called Twofish because we liked Dr. Seuss' book. So that's, I don't know. I don't have a better reason. And Rindall was called Rindall because the inventors were Vincent Ryman and, oh, what was the other guy's name? Dahl was part of the other guy's name, so they combined their names. Okay, so block ciphers. Now, I've been saying you can use block ciphers to encrypt a 128-bit message, but that was actually a little bit of a lie. So here's where I apologize. It's not quite true. If we go look at the definition of security, this IDS definition with a game, what does it count? What do we need for an encryption algorithm to be like considered secure by cryptographers today? And we like work through the implications of that when we use a block cipher. It turns out that a block cipher is not secure by this definition. It doesn't meet the criteria. So let me just refresh your memory about how this game works. In this game, this is security against chosen plaintext attacks. So Eve, the attacker, can choose some messages and get Alice to encrypt them. So there, for those, she knows what the message is and what the corresponding ciphertext is. And then there's a pair of messages, M0 and M1. And Alice is going to encrypt one of those two, and Eve doesn't know which one. And Eve is going to try to infer which one Alice encrypted. Well, it turns out Eve can win this game by first asking for the encryption of, let's say, yes, and then asking for the encryption of no. So Alice learns those two encryptions. And then she now tells Alice, please choose between yes or no and encrypt one of those two. And block ciphers are deterministic. So if you encrypt yes, the same message twice under the same key, you encrypt yes twice, you'll get the same ciphertext both times. So Alice already knows what yes encrypts to. I'm sorry, Eve already knows what yes encrypts to and what no encrypts to. And then she invites Alice to encrypt either yes or no. Whichever Alice does, she'll be able to map that back to the corresponding message. So because block ciphers are deterministic, they don't meet this definition of security. Another way to say it is, if you were to use the same key to encrypt a whole bunch of messages, if two of your messages are the same, they're the same 128-bit value, then you'll end up with the same ciphertext. So Eve, who's observing ciphertext, if she sees 228 ciphertext blocks, 228-bit ciphertext blocks that are the same. She knows the corresponding two message blocks must have been there. That's some partial information about the messages. It's not really revealing what the message was, but that the 7th block of the message and the 133rd message block are the same. That's a partial information leak. It might sound like a really, really minor information leak, but as cryptographers, we're not happy with any kind of leakage, even a very minor. So as cryptographers, we would say, using a block cipher to encrypt your messages is actually not in CPA secure, not good enough. So we would reject this, and we would actually demand a solution to this problem. We want something better. And you might think this is really, really minor, and cryptographers are like super paranoid and like, what the heck is wrong with them? You know, why are they getting so upset about like this really minor, very small amount of information that could possibly be leaked to an adversary in the case where two messages happen to be the same? But it turns out it matters. Let me jump ahead and show you an example. Oh, I guess my example is in the next set of slides. Okay, you get to wait 5 or 10 minutes to show the example, but I'll show you an example in 5 or 10 minutes of why this, what sounds like just a theoretical leakage, actually in some settings could be pretty bad. So block ciphers are actually not secure for encrypting, not even for fixed length 128-bit long messages. They're not secure yet, but they're not far off. And we're going to be able to add a little bit extra to deal with this problem about deterministic, about same message getting encrypted in the same ciphertext. So I'm going to solve that problem in a minute. So just take it on faith for a minute that this will be useful in building an encryption scheme that is secure. So really, we use these block ciphers as a building block, not as like for encryption directly themselves. I thought I'd give you a little bit of just a sense of how AES works, just internally. You don't need to know this for this class, but if you're curious, what you need to know for this class is the API. The inputs are 128 bits, the outputs are 128 bits, the key can be 128 bits or 256 bits, that it's a permutation. But internally, the way this works is it does some operations in a loop. And does a bunch of these operations, and then it does it again and again and again, 10 times. Each one of those 10 times we call a round. And each round itself has some operations, and it like takes some key material and like adds it to the plain text to the input block, or XORs it in. And then it's 128 bits, so that's divided into 8-bit values, 16 8-bit values, and then each byte we look up in a table lookup, a table with 256 entries, with whatever is found in that table. So if the byte value in the upper left was 3, then we look up entry 3 in that table and replace the 3 with whatever table says 3 matters to. And then we rotate around the rows a little bit, and then we do some matrix math on each column, which kind of mixes up data within the column. And then we XOR each one of these bytes with some key material, and we keep repeating this. And so like this operation mixes up the bits within each byte. And then this operation like causes data to kind of move a little bit to the left. And then this operation mixes data within each column. But because things are moving to the left, the next time we do the column, it'll be a different set of bytes. And so eventually, if you keep repeating this, like all the bits start to get scrambled with every other bit. You end up with something where any patterns in the input get all scrambled up, and the output just looks like random bits that are unrelated to the input. Unless you know the key, in which case you can go back. But if you don't know the key, it looks like every output is just some random bits that have no relationship to the input. Tell you nothing about what the input was. And we have no mathematical proof that this is secure. And we're probably not going to have one anytime soon, because it's at least as hard in some sense as proving that P is not equal to NP. So we're probably not going to have a mathematical proof of security, But like lots of cryptographers have tried really hard to find some ways to like break the security of the encryption, and they failed. And I've tried and I failed. So based on that, we kind of guess maybe, hopefully, probably it's pretty secure, we think.
When did you
What's that?
figure out,
Oh, there's a whole bunch of like standard techniques that have been developed over the years for trying to attack block ciphers. And like I used to work in this field for like 10 years and well, 5 years at least. And you'd start to learn all the standard techniques that have ever been useful and against any other block cipher in the past. This one broke Feel in the past, that one broke that other cipher in the past. And so you got this whole laundry list of techniques, and I've tried all those techniques, and I've tried to come up with new ideas and ways to adapt them, and like I got nothing. Everything, each one of them that I tried doesn't work. So I don't know, maybe someone will come up with some new idea. Could happen. All right. So bottom line, block ciphers, they're going to be a tool we're going to use. They let you scramble up the bits in a 128-bit block under the control of a key. You can undo them. Someone who doesn't know the key doesn't learn any information about the input by observing the output of the scrambling operation. They're super fast. And after the break, I'm going to show how to use them to build encryption algorithms. Okay, so let's take a break, have some snacks, take a 5-minute break, cool off, walk around, whatever you need, and we'll reconvene in 5 minutes. Okay, let's reconvene and get started again. So I've been talking about block ciphers, which are somehow not satisfactory. And I've been asking you to take it on faith that they're useful nonetheless. And so now I'm going to show you how to use them to do what we actually want to do. It's kind of a weird way of teaching. I show you a whole bunch of things that are not actually useful directly. Okay. It is so hot. Totally, man. And it's in here too. It's like, it's nice out there. So what I'm going to show you is, it's called modes of operation. A mode of operation is a way of using a block cipher to get a secure encryption algorithm. And the mode of operation is going to have two things to do. The first thing to do is it's going to have to solve this problem with block ciphers that they're not secure because they're deterministic. It's going to have to solve the problem of encrypt the same block twice, you get the same output twice. That's the first thing a mode of operation is going to have to do. And the other problem that a mode of operation is going to solve for us is I want to be able to encrypt a message of any length, not just 128 bits. That's the other thing a mode of operation is going to do. And it's going to be built out of block cipher, using a block cipher. So let's think about how we could do this. Let's imagine that I wanted the longer messages. Should we start there? That's a fine place to start. Let's think about how to encrypt longer messages. If I have a message that's longer than 128 bits long, like I have a 256-bit length message, and I want to encrypt it, and I have a block cipher, what could I do? Any ideas? Yeah. Love it. Let's use it multiple times. The first 128 bits of the message will encrypt with the block cipher. The second 128 bits of the message will separately encrypt with the block cipher. That's a kind of a natural thing to do. What are you thinking? How come? You're worried if we use the same key for too many messages, then
You can send test messages.
then maybe an attacker can like learn some of this mapping. And the more we use the key, the more the mapping the attacker learns. It's sort of not that big a deal because there's 2 to the 128 possible plain text messages. And so to learn the whole mapping, if you use the same key for 2 to the 128 messages, you'd certainly have a problem. But in practice, no one's going to use a key for that much. I've probably, I've never sent that much data off of my laptop in my entire lifetime. Yeah. Yeah. There would be an issue. Wouldn't there be an issue if the first half of the message is the same as the second half? There would be, right? Because if the first half of the message is the same as the second half and we just encrypt them separately like that, then the ciphertext, the first half of the ciphertext is going to match the second half of the ciphertext. And the eavesdropper is going to be able to tell that the message had this. So there would be an issue. So this kind of gets back to the other problem that we needed to solve, which was the problem of this being deterministic. So I like it. That would be for encrypting longer messages, except we haven't yet solved the problem of the deterministic business. Does anyone have any ideas for anything we could do about the deterministic problem?
That's a way to like a seeded pseudo-random number generator.
Okay, that's clever. That's clever. I like it. Use a seeded pseudo-random number generator. We'll come back to that later in this class. Remember the word stream ciphers. The tricky bit is that pseudo-random generator becomes very critical. And you have to design that very carefully. And I kind of don't want to have to invent any new concepts like figure out what makes a pseudo-random generator secure or not. I've got a block cipher. I just want to use that. So we'll come back to it. It's a good idea, but it's not the kind of approach I'm looking for right now. So let's keep brainstorming, but I like it. Yep. Might be. It's usually the plain text and ciphertext are 128 bits. And then you can use a 128-bit key or you can use a 256-bit key. Can I use the ciphertext as a key? Oh, I like it. I like it. I like what you're trying to do. You're trying to make sure that the second half of the message gets encrypted differently because you're going to maybe use the first ciphertext block as the key for the second. But that's not any good, right? Because you can't use a ciphertext because the Eve knows that ciphertext, and so then they'll know what key you're using if you use the ciphertext as the key. That's no good. Maybe we use the plain text as the key, but it turns out, oh, that's not so good either because sometimes messages start with a very like a base a common prefix that the eavesdropper could know. And then they know if you use the plain text as your key for the second part of the message, then the eavesdropper can guess what key is being used for the second. So that's not so good either. But I like what you're trying to do. I'm asking you to like solve a hard problem. So it's really not fair of me to ask, but yeah.
Did you run your block encryption on the key itself to get like a new random key for the next block?
I could try to do something like that, run the encryption on the key itself to get a new. Yeah. And then I get a bunch of different keys. Yeah, you could do something like that. Yep. Uh-huh.
The whole purpose that we did, get another random.
Going to solve the problem of being deterministic with a random value. So we get another random value. So that's a reasonable way to solve determinism, is to add some random value. Make sure that every plain text we encrypted with the block cipher was different. We could make sure that we didn't about this weakness of block ciphers. How could I combine if I had a random value and a message value, how could I somehow combine or put those together to get an input to the block cipher so that I can be sure I'll never send the same input to the block cipher twice? Does anyone have any ideas? Yeah.
What about like rearranging the parts of the plain text? So like then send a different order and then you pretty much plug it into the block cipher.
Reuse the random value to like reorder the bits of the plain text. Yep, that could be one way. Yeah.
You do that, like even like what's the random data you send it out with the.
Yeah, we got to worry about how we're going to decrypt. Good point. So let's make sure that the recipient can decrypt. One reasonable thing. How could we make sure that the recipient knows the random value? Yeah. What's that?
Send it to the end of the message.
Send it to the end of the message. Send it to them, or send it to them encrypted. So Alice can pick a random value and send it to Bob, and now they both know the random value. So the random value might not be secret, but it might be different every time, because it's unlikely if I'm picking random values, I'll end up with the same value twice. So what's another way I could combine a random value and a message to get some combined thing?
Maybe all.
Alternate. Alternate. Say more.
In one bit, you have the first bit of the message, and the second bit, you have the first bit of the random value. So
Okay, we get alternate bits. First bit is the first bit of the message, the next bit is the first bit of the random value, then the second bit of the message, second bit of the random value.
yeah,
And in 128-bit input, how many bits would be random and how many would be message? 64 and 64. Yeah. So that would work. Another equivalent way to do that would be to say this first 64 bits of the input are a random value and the next 64 bits are a message. Yep. And then it's pretty unlikely that we'll end up with the two inputs to the block cipher being the same, because that would only happen if the same random value was chosen both times. Yeah.
Homework. Expert.
Use XOR. So that's another way you could do it. How could you use XOR?
XOR the text.
XOR the message and the random value.
Or I think in the homework, ask the initial values through the cipher first, and then XOR that next part of the chain. I don't know.
Yeah, there's some funky stuff happening. Yeah. Yeah.
One I had ideas.
Could we use a one-time pad idea with this? How would you use the one-time pad idea?
XOR.
Ah, pick a random pad. Alice picks a random pad, XORs the plain text with that random pad, and then encrypts that randomized thing with a block cipher. I think that would avoid our problem of having, it's very unlikely that you'd have two inputs to the block the same, because I've randomized it. If I were to send an all zeros message that has 1,000 0 bits after you XOR with a random pad, it's unlikely any pair of 128-bit blocks will be the same. How do we get the one-time pad to the recipient? Let me give you some options. One option is Alice sends the one-time pad to the recipient, unencrypted. Can anyone give me another option? Yeah?
Block cipher on the random.
Use the block cipher on the random pad on each 120 bits of the random pad. So send it kind of encrypted to Bob. All right, let's see what you all prefer. Do you prefer to send that pad unencrypted to Bob? How many prefer to send it unencrypted? How many prefer to send it encrypted? All right. Someone give a plausible reason why it might be better to send it encrypted. Yeah? She could maybe try to what? If Eve knows the padding scheme, maybe that reveals something. So let's encrypt it. Would it be fair to say, let's encrypt it to be safe? That way I don't have to worry about what Eve could infer if she knows this pad? Is that fair? I buy that. If you give me a choice of encrypting or not encrypting, encrypting seems safer. Okay, what about, so I think you're on a good, I think you've got a good idea. I think this would work. What about without encrypting it? Would that be secure? So the scheme is Alice picks a random pad, the same length as the message. She XORs the message with the pad. She encrypts that XOR with the block cipher, each 128 bits of it separately encrypted with the block cipher. And then she sends the pad in the clear, unencrypted, to Bob as well. Do you think that would be secure? Okay, let's take a vote of just what feels like maybe feels right, just gut instinct. Gut instinct, not secure. Gut instinct, think it's secure? My gut is silent. How could we tell whether it's going to be secure or not? What problem were we trying to solve? What's the security problem we were trying to solve with just encrypting each block with the block cipher independently? Yeah?
Oh my god.
Yeah? How could we tell? I don't want the answer, just how could I tell whether it's secure or not? Do you want to answer? You want to answer? Okay, I'm gonna let you stew. Does anyone want to give me an idea how you could approach this? How could you figure out whether it's going to be secure or not? Yeah?
Right, so the issue before was like, you send something, you see the block cipher encryption, then you send two messages that one of them is the one that you just saw the encryption. And then you can see like, if it is that one, you've seen the encryption. So like now if you're XORing it and the XOR is random each time, then it'll be XORed with something different the second time. See it?
Okay, I like the way you're thinking. So I'm gonna rephrase or paraphrase what you said. The problem we had before is feed the same input into the block cipher twice, you get the same output both times. And that's the problem we're trying to solve. So let me suggest that maybe a way to try to analyze whether the scheme you just proposed is secure is to figure out whether it has that problem. Could we end up with the same input to the block cipher twice? Are we gonna have leakage of information because block ciphers are deterministic? So why don't you talk to someone sitting next to you and figure out whether this scheme is secure. Pick a random pad of the same length as the message, XOR the message with the pad, encrypt the XOR, send the pad unencrypted. Talk to someone next to you. Do you think it's secure?
That would be it. Yeah. Actually.
We have a certain bias to block.
That's the same problem. Let's add. Which had
Yes, exactly. How are you doing that?
Basically, but this one's public.
Yeah.
Because they know that that's real, because if they don't know that either you can just stay with something.
Right.
I think you have, yeah. But it's like.
It's like, it's not like, it's just stuff that I would.
Let's check where we're at. This is a hard one. How many say, I think it's secure? How many say, I think it's not secure? Okay, good. Does someone want to give me a reason, a plausible reason why someone might argue that it's not secure? I don't need it to be right or wrong. Just give me a plausible reason someone might argue it's not secure to do this. Uh-huh.
Better do the. You're encrypted anyway.
Okay. Uh-huh. Okay. Although I'm not 100% satisfied with that answer. That says I'd rather encrypt it if I have the choice, but it doesn't really tell me whether it's secure or insecure if I don't encrypt it. Yeah?
My first thought was that we were kind of just running into the problems that we were talking about before with other TP.
Uh-huh.
And then, Ellie was able to kind of convince me like why it's secure. But then I thought about like the functionality of it as well. So like kind of thinking again about the human aspect of it, like we'll just you would have to keep changing it, but not.
Okay, so a worry is that we might have similar problems as the one-time pad. Okay. Does anybody want to give a reason why, a plausible reason why it might be secure, or why you could, maybe an argument you could make why it's secure? Yeah?
If you're randomizing the key like every time, the issue before was that it's deterministic, but the only way it'll ever be deterministic is if you send it with the same key. And then, so if you're just randomizing the key every time, then every message, even if it's the same message, will come out completely different.
We're randomizing things so every message will come out completely different every time, even if I send the same message twice. Yeah?
I just thought of why it may not.
Okay, why it might not be?
The extra operation is permutation.
XOR operation is
Commutes the permutation.
commutes with a permutation.
That's, yeah.
Oh, okay. This is a tangent, but just beware. We have the different kinds of reordering of the bits, but there's permutation of bit strings. It doesn't commute with the block cipher. We might have to talk about that afterwards. Yeah, I think I know where you're coming from. Maybe let's try to calculate it this way. Suppose that I'm encrypting a message that is 256 bits long, so it's 2 blocks. And I want to know what are the chances that the 2 inputs to the block cipher are the same. That's where I get into trouble. If I ask the block cipher to encrypt the same 128-bit value twice. So what are the chances that the 2 inputs to the block cipher are the same in this scheme? Does anyone know how to calculate that? Does it depend on the message, the particular message that I'm sending? Yeah? The one-time pad would have to be the same? With the one. Okay, so let me see if I get what you're saying right. If the first half and the second half of the message, the first 128 bits of the message and the second 128 bits of the message are the same, then I'll only end up with the same inputs to the block cipher if the one has the same first 128 bits and last 128 bits. Is that, am I getting, did I get you right? Okay, what's the probability that happens? Yeah, 1 over 2 to the power 128. If I choose a random 128-bit value and another random 128-bit value and I ask the probability they're the same, if they're random, it's 1 over 2 to the power 128. So if I'm encrypting a message where both halves are the same value, but I'm doing this one-time pad thing first, then there's only a chance 1/2 to the power 128 that you get the same inputs to the block cipher. And there's some leakage happening. And if it's not the same inputs to the block cipher, there's somehow no leakage in some sense. Do I need to worry about a probability of 1/2 to the power 128? No, why not? Is that like a likely or unlikely? Like it's infinitesimally small. Yeah, yeah. I looked up during the break the chances of getting hit by lightning over a 1-year period, and what I found said about 1/2 to the power 21 chance. So much, much less likely than the chance of getting hit by lightning. So from an engineering perspective, events of probability 1/2 to the power 128, we can consider them almost impossible. Like I don't really need to worry about them. So basically, what you've shown with this calculation is it's very unlikely that you will run the block cipher on 2 of the same inputs. So this scheme that you just mentioned, that you proposed, randomize the message by XORing with a random one-time pad, would solve the problem we have of the block cipher being deterministic and would make the scheme secure. It has a little bit of a downside that it now doubles the information that must be sent because you have to send both the pad and the ciphertext. So you increase the size of messages by a 2-fold factor, which is maybe not good from a performance perspective, but it would be secure. It would let me encrypt any length message, and it would solve the problem of the determinism. So that's a great scheme, and you don't even need to encrypt the pad. Turns out you can do better. You can do better without even needing to have a whole long pad by kind of a tweak, a variant on your idea, so that you don't have to send a whole long pad that's equal to the length of the message. It's enough to send a random value that's just 128 bits long. And the way we're going to do that is for the first block of the message, we're going to randomize with a random value, this pad. And for the later blocks, we're going to get a random value from the ciphertext. And it turns out that's going to be okay. All right. So let me walk you through in more detail some of these modes of operations and which ones are good and which ones aren't and how to solve this problem. Hopefully this kind of gave you a sense of what's involved in designing a mode of operation and what their purpose is. So the simplest mode of operation you might come up with, what you proposed half an hour ago, was encrypt each block of the message independently, separately. That's called electronic codebook mode. So we take the message, we break it up into 128-bit chunks, and we apply the block cipher to each one with the same key. And you get a bunch of 128-bit ciphertexts, and you just concatenate them, and that's the encryption of the message. And this is not secure, because if the first and the second 128-bit chunk of the message repeats, is the same, then Eve can observe a repeat down here and tell that the message had that structure. And to give you some, I told you I would give you some intuition for why this is not just a theoretical problem, but in some cases can actually be a very severe problem. Here's an example of encrypting an image. So take this file, take this image, like save it as a file, uncompressed, and encrypt that file. And let me show you a visualization of what you get if you encrypt that file with ECB mode. You might notice that it's not a nice looking penguin, but you can still see the broad shapes of the penguin. Why is that? Yeah? when the pixel values are the same, I'm running into this problem of same message, same ciphertext.
Yeah, well, the only two one key for all of them. It's like just a set permutation of pixel values instead of the actual. Just means that like this black pixel then becomes this new set of values, but every black pixel becomes a set of values. So you'll retain the relationship between pixels in the image, but the values of them. Yeah. I don't think eight. Is there like I think that you can define how big the cipher value and really
Maybe I would explain it this way. Think about a chunk of, I don't know, 6 or so white pixels in the upper left, totally white. When you, in an image file, that's maybe 16 bytes or more of data. Think about another chunk of 6 pixels in the, when you store them in an image file, that's another chunk of about 16 bytes or so. And it's the same 16-byte value, even though it's 2 different locations in the image because they're both all white. So the upper left encrypts under the block cipher to the same thing as the lower right. So this white region where it's all white is going to encrypt to ciphertext blocks. It's a lot of ciphertext blocks that it's all the same ciphertext. And that's why you can see these patterns here. The white region pretty much all encrypts to the same thing. So there's a lot of leakage that can happen if you use ECV mode. So don't use ECV mode. This is no Buddhism mode. It is not NCPA secure, and it is not secure in practice for some kinds of data. So that's why we can't just encrypt each block separately, and we need something fancier. So a fancier method is to use some randomness. And the name in the literature, for whatever reason, is initialization vector. This is just a name that's given to a random value. This is a random value that's chosen randomly. Each time you want to encrypt a message, you choose a new random number. This is 128 bits long, same length as the block length. And it's like the pad in the scheme you're just like pad. Same thing, just a different name. And that gets exclusive board with the first block of the plaintext. So the first block of plaintext is randomized now. And then we encrypt that randomized value. We encrypt the XOR. We need to do the same for all the other blocks of plaintext. So we need a random value. But instead of choosing another random value for each block, it turns out what you can do is use the previous ciphertext block as your random value, because the output of a block cipher will be random. The intuition is it's kind of random looking. So we're going to reuse that as our like add or value to XOR in for the next block, and so on. So we're doing an engineering optimization on your one-time pad idea. And then to enable the recipient to decrypt, this initialization vector, this random value, needs to be sent unencrypted to the recipient. So the encryption of a message now is obtained by breaking it up into 128-bit chunks, picking a random initialization vector, encrypting each chunk with the block cipher as shown here, and then you concatenate the initialization vector and all of these 128-bit ciphertext together, and that is the full ciphertext, the encryption of the message that is sent to Bob. Okay, so this is called CBC mode. And if you want, you can verify for yourself that the recipient Bob will be able to decrypt if Bob knows the key. The initialization vector is sent in the clear, so Bob knows that value, that random value. Bob can take this ciphertext and decrypt with the block cipher and get back this value right here after the XOR. And then because Bob knows the initialization vector, you can remove the initialization vector in the same way you decode a one-time pad. XOR this value with the initialization vector and recover the plain text. And similarly, Bob can decode this ciphertext and XOR it with the previous ciphertext and get the second plain text block and so on. So the recipient can decrypt. Do you have a question? Oh, why not make a larger block cipher that could handle messages that are longer than 128 bits? Is that what you're asking? Yeah. That could be another strategy, but it might be pretty painful because I would need one for 256-bit messages and one for 384-bit messages, and I'd need a whole lot of block ciphers, one for every length, and I'd rather just design one and vet that one really carefully rather than have to design 1,000 of them for different lengths. That'd be harder to analyze. I don't know. That might be a workable strategy too. This is the one that the field has settled on as something that works. There might be many other ways that could work too. Yeah. So I don't really have a good reason why not. It's just that we haven't done that. Okay. So you can decrypt. Another interesting thing about CBC mode is for efficiency, it turns out that decryption can be done in parallel. You can decrypt each block in parallel if you have a lot of multiple units that you can use for decrypting in parallel, but encryption is sequential. That's not that important. And I want to say something about the security. The security of CBC mode. If I encrypt two messages that start with the same 128 bits, is that going to be detectable? Is Eve going to be able to detect that I sent two messages that start with the same 128 bits? No, why not? Yeah? It's randomized with the initialization vector, and for each message, a different initialization vector is chosen. So for the second message, probably it'll have a different initialization vector than the first one. So the input to the block cipher will probably be different for those two. And so their outputs will be unrelated. Yep. Okay, so this solves the problem of sending two messages that start with the same 128 bits. What if I send one message, but the first 128 bits is the same as the second 128 bits? Is that detectable by an eavesdropper? Can an eavesdropper look at the ciphertext and tell that the message had that structure? How many say yes, an eavesdropper could infer whether or not the first and second block of plain text are the same? How many say yes? And how many say no, an eavesdropper couldn't infer? And why not? No is correct. Yeah? I've exhausted you all. We've been going a long time. Does anybody try? Anybody who hasn't spoken much? Do you want to give it a try?
It's like, since you pass it through both sides. Like, it's basically the same thing as having a new initialization, but it's like that.
It's the same thing as if your second block had a new initialization vector. So they're both randomized. And probably this value, the vector, will be different from the value used for the second block. So probably you won't have the same input to the block cipher in the first block and the second. Okay, so that's CBC mode. What about, there's a detail that I left out. There's a detail that I just passed. I said divide the plain text up into 128-bit chunks. But what if the plain text is not an even multiple of 128 bits long? What if the input's like 150 bits long? And the hint is the answer is going to be padding. So with that hint, what could I do if I have a message that's like 150 bits long?
Just, it's,
Throw some more garbage bits at the end. Throw some more garbage bits at the end. Oh, how would the recipient know how many garbage bits to remove? Oh, yeah, it's a little tricky. We got to make sure the recipient can decrypt. Yeah.
Might be kind of part of the key, so like adding a number, like. If it's 8 garbage bits, adding eight, or something.
Oh, yes. Brilliant, brilliant. Okay. I love it. I love what you came up with. Maybe a way to tell the recipient how many garbage bits there are would be to add something more to the ciphertext, a number to the ciphertext that says, this is how many garbage bits were added. That would be very simple, right? It would require sending another value. And so you came up with a very clever scheme that avoids the need to send another value. Which is instead what I could do is I could pad with some bytes. Let's assume the plain text is a multiple of bytes long, multiple of 8 bits long. If I need to add one garbage byte, I add the value 0, 1. If I need to pad with 2 garbage bytes, I add a byte containing the number 2 and then another byte containing the number 2. If I need to add 3 garbage bytes, I add a byte containing the number 3 and then a byte containing the number 3 and then a byte containing the number 3 and so on for however many bytes I need to add to make this up to a multiple of 128 bits long, up to a multiple of 16 bytes long. I add some bytes containing that number. That was your scheme? I love it. How does the recipient decrypt and know how many garbage bytes to remove? Yeah? Look at the very end of the decrypted message, look at that last byte, and that number will tell you how many bytes to remove. So this is a very clever, so both of your suggestions would work. Both of these schemes would work. The nice thing about your scheme is that it doesn't require adding any extra numbers to the ciphertext. The recipient has everything they need to know just by looking at the decrypted value. Yes, so those are called padding schemes. These are ways that the sender can add some padding, add some extra bytes, some extra garbage bytes to make it a multiple of 16 bytes long, and a way that the recipient can remove those. Question?
Talk about,
Doesn't
the homework to talk about a way to break the second?
work? Okay, what is the homework doing? The homework going to break this. In the homework, you're looking at this crazy thing. I've been talking about security against an eavesdropper or an eavesdropper who can do chosen plain text attacks. There are some settings where an attacker can also do chosen ciphertext attacks. The attacker can send a corrupted ciphertext to the recipient and see what the recipient does with it or observe what it decrypts to. And the homework is exploring what that enables if an attacker can do this kind of chosen ciphertext attack. And I am ignoring the problem of chosen ciphertext attacks in this lecture. I'm focusing on schemes that are secure against an eavesdropper, secure against chosen plain text attack, but as you'll discover in the homework, might not be secure against chosen ciphertext attack. And that's a little bit of a setup for a future lecture where we're going to talk about how to solve the problem of chosen ciphertext attacks. But I'm not going to worry about that today. Yeah. All right. So padding schemes are a way to make sure that you have a multiple of 128 bits. And there's a bunch of different ways to do it. But basically, they all involve adding garbage bytes until the message is a multiple of 128 bits long. It's a little bit tricky. It's a little bit tricky to do if we want to make sure the recipient can remove those padding bits without any extra information. Like if we just pad with all zeros, it may be hard to tell how many 0 bits to remove. So we need a way that can be removed without ambiguity. So one way is exactly what you proposed, and that has a name, and there's a standard. It's called PKCS number 7. And another way that works is you can append a 1 bit and then as many 0 bits as needed to get to a multiple of 128 bits. And then the recipient can start removing 0 bits and then remove a single 1 bit, and then they know they're done. So there's many ways to do it. They're all equally valid, all equally good. It doesn't matter. Choose any of them. They're all fine. Just have to make sure that both Alice and Bob are using the same scheme. Okay. So the bottom line is, if you use the CBC mode of encryption with the AES block cipher, with one of these padding schemes, it now solves all the problems we've talked about. It gives you an encryption algorithm that is in CPA secure, that doesn't have any of these inches, and is like super fast also, which is really nice. Okay, so this is now the payoff for why I was showing you all these schemes that didn't work, because it's blocks that then enable building a scheme that does work. So AES block cipher encryption in CBC mode with some padding scheme would be a standard way to do symmetric key encryption. And it's secure against eavesdroppers and secure against chosen plain text attacks. But you have to make sure that the initialization vector is chosen randomly for every message. If you were to like use the same initialization vector for every message, no good, right? You've lost your security. You're back to the deterministic information linkage world. Okay, so we found a solution to the symmetric key encryption problem, AES and CBC. Let me pause here and see if there are any questions. Yeah.
Zero, the one being at the end of your text message. So if you zeros had it to the end and then one right next to the word.
Yeah, append a 1 to your plain text messages and then append a whole bunch more zeros after that.
What? And I can imagine there would be a plain text message where the bit string is 1 and then the length of it chunk of meaning.
Yeah, what if you see 10100? What was the plain text?
I'd assume 1 0.
Yes,
The one was 1 0 1.
that's the same as what I just said.
No, but
Oh, if the plain text was 10100? Yeah, the sender always adds a 1 and some zeros, always. So the recipient always removes one of those.
so
If you started with 17 of them, you now have 18, and then the recipient removes back 1 and they're back to 17.
we'll say for this case it's 128 bits long.
Yeah.
If it ended with 1 0, like 100, you have to add another 28.
Yeah.
127 zeros.
Exactly. There is this funky special case. What if my message was already exactly a multiple of 128 bits long? Am I done? No, I have to add a whole nother 128 bits of padding. Yeah. Yep.
At like three bytes.
Yeah, why can't we just send in the clear, send the number of bytes to padding?
Yeah, but like,
Is there a problem with that, you're asking?
yeah, I was wondering like if you have like 3. How do you know that like 3 isn't like part of the message? Like, if you put like 0, 3, 0, 3, 0, 3 at the end, and the message also maybe contains something like.
If I've added 3 bytes of padding to the end of the message, 030303, and the message also contains ends with some 303 bytes, how do I know which ones are the padding, which ones are the message? The answer with this padding scheme is you look at the last byte of what was decrypted. If that's 0, 3, you know there's 3 padding bytes. So you move just the last 3 bytes.
I don't think you have to do all like. Says that they would have-
Yep. Yep. So you're always adding padding. You're always adding at least 1 byte of padding, always adding between 1 to 16 bytes of padding. Yep.
Adding to get applied next to the second.
To the plain text before encryption. Yep.
Right, message is 7 hiding byte, right? No, bunch of garbage and 1 byte.
You always add padding. So if you have a 128-bit message, you have to add another 128 bits of padding. So it's split up as your 128-bit message and then 128 bits of padding in whatever format your padding scheme says to use. No, there's you have a whole long message. Before you break it up into 128-bit blocks, you add padding. So it's a multiple of 128 bits. So there's 1 padding at the end of every message. All right, so CBC mode, it turns out, is secure in this in CPA sense, and one can prove it. You can actually write down a formal mathematical proof. And what the mathematical proof says is if the block cipher is secure, it's this, under this, random permutation, pseudo random permutation definition I gave earlier, then CBC mode encryption is secure in the in CPA sense. And that's proven by a reduction. So if you've done NP completeness reductions, it's the same kind of concept. Prove that if any attacker could learn anything, could win the in CPA game against AES CBC mode encryption, then there's another attacker that could break AES, meaning distinguish it from a random permutation. So under the assumption that AES is indistinguishable from a random permutation, it follows that CBC mode encryption is in CPA secure. So what that tells you is no guarantees that AES itself is secure. We think, but we really, really think it is. And assuming we're right about that, then the mode of operation is good. Takes care of all the remaining issues. So that's kind of nice to have like a proof that tells us that this is a good design, that this is a satisfactory design. And if we try encrypting the same image file now under AES CBC mode encryption, no more discernible patterns because each block is using a different randomization. So even when you have 2 white chunks that are the same pixel values, they have different randomizations and different inputs to the block cipher, and so unrelated outputs. Okay. I think this is a good time to take a 3-minute break before we continue. Do you think so? Let's take a 3-minute break. Stretch break, walk around, whatever you need. Okay, let's reconvene. Let's reconvene. I want to show you another mode of operation that is also secure. It's also secure. You can use either CBC mode, which we already saw, or this other one I'm going to show you. And this other one is inspired by your suggestion that we have a pseudo random number generator. That we take our key and we somehow expand it to a lot of random bits. And the motivation here is the one-time pad. Remember the one-time pad we said is perfectly secure, but it required these very long keys and you couldn't repeat them, and that was super annoying. So what we're going to do is we're going to try to come up with a way that's sort of like that, but using a block cipher. So assume that I've got AES block cipher and I've got a 128-bit key. Alice and Bob have pre-shared. And now I want to do something like a one-time pad. I want to generate the pad, though, with my block cipher. The pads might need to be very long because the messages might be very long. My AES key is only 128 bits. Do you have any ideas how I could generate a really long pad if I had a block cipher AES and an AES key? I want to encrypt a 1,000,000-bit message, so I need a 1,000,000-bit pad. One-time pad says I have to generate it randomly, but I'm not willing to do that. But I do have a 128-bit key that's been shared between Alice and Bob. How could Alice and Bob generate a 1,000,000-bit pad? Yeah?
Text of the key itself, the encryption cipher, and then just keep doing that over and over until you get random.
Feed the key in to the block cipher, feed in some plain text value, and the output will be some random looking thing. And keep doing that over and over again to get as many random looking values as you need. Yeah, that would work. If you want to, after class, look up OFB mode. You invented OFB mode. That's a known thing. Any other ideas? Other ways you could do it? Yeah. Multiply. Oh, what would you multiply? Multiply the original plain text and the site and the key. Yeah, okay. That would be something not quite a one more. I'm not generating a pad and then trying to do one-time pad XOR, but instead you're going to multiply the plain text times the key. Maybe modulo something so that the numbers don't get too large. Is that the idea or no? No modulo. Yeah. Okay. Multiply the key times the plain text. Okay, this would be a different kind of scheme, but that's worth thinking about too. That'd be an encryption scheme. Multiply the plain text times the key, modulo something. Could you decrypt? Modular division. Divide by the key. Like compute the modular inverse of the key and multiply by that. You could decrypt. As long as the key is relatively prime to the modulus. Yeah, you could decrypt. Unfortunately, it turns out it would not be secure. It has a similar problem as the one-time pad. So good try, but it turns out it's not any more secure than a one-time pad. One-time pad uses like addition or XOR. You're trying to use multiplication. Multiplication is somehow not that much better than addition. So I like it, but it's not secure. And if you wanted, we could like in office hours work out together what the attack on it is, why it's not secure. So I suggest we stick with a one-time pad because we know the one-time pad, if our pad was random, it would be secure. But what is there a way I can get any other ways you can think of for generating a pad? They'd be sort of random like if you had a block cipher and a block cipher key. If you don't have any other ideas, that's fine. I just want to give you a chance to brainstorm something. I'm going to show you something that's called CTR mode. Does any guesses what CTR stands for? Turns out it's short for counter. Counter. Does that give you any ideas for? Yeah,
Like storing like the ciphertext to the input.
storing the ciphertext with the input. I want to do a one-time pad. So I want to generate from the key, somehow generate a pad. And then I'm going to take that pad and XOR that with a message to get a ciphertext. So the challenge is, how do I get the pad? Yeah.
Then block cipher, and then keep that, and then that is the one time, like it's keep the counter, so that way we can make it another time pad, still.
That's a very reasonable way. And that's how counter mode works. So in counter mode, we encrypt a counter. We have a counter, like maybe it starts at 0. And we encrypt 0. And then we update the counter to 1 and we encrypt 1. And then we update the counter to 2 and we encrypt 2. And we update the counter to 3 and we encrypt 3. We get a bunch of outputs from AES that are random looking, and we concatenate all those together, and that's our pad. So counter mode, the actual counter mode does something a little fancier. We got to get that maybe we want an initialization vector in there somewhere or something. So in counter mode, we actually have a provision, the official counter mode, there's a provision both for an initialization vector and a counter. The actual standard scheme has the input to AES being 64 bits that are what's called a nonce, and 64 bits that's a counter. And the nonce is chosen to be different for every message. And the counter, but the same nonce is used for all the blocks in the same message. And then the counter increments inside the message. For the first block of the message, it's 0, and the next block of the message, it's 1, and the next block of the message, it's 2, and so on. And we concatenate the 4-bit nonce and the 64-bit counter, and we get a 128-bit value, and we encrypt that with AES. And the output will be some random looking thing that's unrelated, has no obvious relationship to the input. And then we encrypt with the next counter value, and the output will be some random looking thing that has no obvious relationship to the input or to the previous output. Inputs, and we concatenate them, and that's our pad. And then we use that as our pad for a one-time pad. And because the outputs of a block cipher look random, it sort of looks like you had generated the pad at random. It's not truly random, it's generated in a systematic way with a block cipher, but for someone who doesn't know the key, there's no patterns in there that they could use that would like show that this is anything different from random. It's as good as random in some sense. Yeah. Sorry, I couldn't hear you.
How did we decide like how much space we allocate for like the nonce versus the counter?
How did I decide how much space for the nonce versus the counter? Yeah, it was kind of arbitrary. The counter, the requirement is there has to be enough space for the counter so that for a possible message I could ever anticipate encrypting, the counter will never wrap around. Because I want to make sure that I never feed the same input into this block cipher twice. So the counter value is going to be different for every block within the same message. So if I choose a 64 for the counter, I can handle messages, encrypt messages that are up to 2 to the 64 blocks long. That is more than enough. So 64 bits is more than enough for the counter. And for the nonce, I need the requirement is that the nonce needs to be different for every different message you encrypt. So with this scheme, you can encrypt up to 2 to the 64 different messages and choose a different nonce for each one. And then you'll run out of nonces and you can't use that key anymore. And that seems like more than enough too. There's no way I'm going to encrypt, like there's no way I'm going to send 2 to the 64 messages in my lifetime. That's a ridiculous large number of messages. So it's just kind of overkill. 64-bit seems like more than enough for both, so good enough. Okay, so this is counter mode. This is how counter mode works. We use AES to generate a pad, and then the pad gets exclusive ORed against the plain text. How do I decrypt? What does it look like? What does the decryption process look like for Bob, who's receiving one of these? When Bob gets a ciphertext and Bob knows, what does Bob know? Does Bob know the ciphertext? Yeah. Does Bob know the key? Know the key? Yeah. Does Bob know the nonce? Ooh, I didn't show that here, but yes, the nonce has to be sent into clear. So Bob knows the nonce. Does Bob know the starting value of the counter? Yeah, it's always 0. So how does Bob decrypt a ciphertext and recover what the original message must have been? Yeah? Regenerate the pad and then decrypt the same way that you decrypt a one-time pad. And the pad depends only on the key and the nonce. So Bob can do the same thing that Alice did to generate the pad. So I hope maybe this illustrates now how this fits into this kind of proposal that you made earlier of a pseudorandom number generator. We're using her as a pseudorandom number generator. And both encryption and decryption can be parallelized, which is when applications use counter mode, because it allows really, really fast encryption and decryption. If you have like hardware support for this, you can 16 decryption blocks in a chip and they all run in parallel, and each block of your message gets encrypted or decrypted in parallel. Do you need to pad messages? This is a kind of nice thing about counter mode. No, you don't need to pad messages anymore. Just truncate the pad to be the same length as the message and cut things off. So that's kind of nice. And there's a proof that the counter mode is in CPA secure, assuming that the AES is secure and that nonces are never repeated. I wrote up here that nonces are randomly generated, but actually it's enough that nonces are different. Nonces don't have to be randomly generated. That's just one way to make sure that you get different values. You could use any way of getting nonces as long as each message has its own nonce. So a nonce and an initialization vector are almost the same thing. It's weird. We have these two names for what's almost the same concept. The only difference between the two is an initialization vector is supposed to be generated randomly, and a nonce can be generated any way you like as long as it doesn't repeat. Random is one way to get a number to make a repeat, but you could use some other way. Like a counter or something would also be okay. And a way to remember that if you have a hard time remembering the distinction between an initialization vector and a nonce, you can think of nonce. I'm not sure if this is actually where the name came from, but maybe number used once, n once. But the dangerous part about counter mode is if you ever reuse a nonce, it's like a two-time pad. It's like reusing a pad in a one-time pad. If you use the same nonce to encrypt two different messages, You'll end up with the same pad both times. And it'll be just like encrypting two messages with the same one-time pad. And that's very, very bad. Often it allows an eavesdropper to recover both of those messages. So the counter mode has a bunch of advantages. It's like simple, easy to use, very fast, but it does have this fragility. If by mistake you use the nonce twice, it's like really, really bad for security. Here's an encryption of a penguin image, the same image in counter mode. You can see, again, no patterns persist through. That's because the pad values are like random values. They're indistinguishable from random. And so even though you have the same parts of the white chunks, they get encrypted differently because they have a different pad. So now with that background, I can now tell you, remember I mentioned a lecture or two ago about the mistake that was made in 61A exam tool that allowed someone, if they wanted, to like decrypt exams before the start of the exam date. The TAs who wrote this took this class and they used a off-the-shelf Python library, and they're like, AES I know is good, counter mode I know is good, so I'm going to encrypt all the exam questions with AES counter mode. And they were distributed to everyone before the start of the exam. And then the time when the exam starts, then they sent just the key. It was this very clever design. Their first design was when the start of the exam happens, send everyone the text of the exam. But the text of the exam might have been like, I don't know, tens or hundreds of kilobytes. And there might be 1,000 people in 61A at the time. And the network just like got overloaded trying to send them all. And some people were like, I didn't get my exam until 5 minutes later. And they're like, ah. So the solution was send everyone early the encrypted exam. And then at the start of the exam, send everyone the key. And the key is much shorter. It's great, very clever scheme. But the mistake they made was they called this library, this library to do AES counter mode encryption, which is good. That's good. You shouldn't implement it yourself. Use a library, someone else who got this right. And they assumed, counted on the library to generate the IV for them. But what they didn't know was that this library had a default that if the caller doesn't specify an IV, it didn't generate it randomly for you. It used all zeros as its default. And so therefore, every question was being encrypted with the same key and the same IV, same all zeros IV, so the same pad. So if there were 10 questions on the exam, it was like the 10-time pad. So it's completely insecure, and it's totally possible to recover all the exam questions given the ciphertext before the start of the exam. Security was completely lost because this library had bad defaults, and the people who were writing it didn't realize the bad defaults, didn't realize whose responsibility it was to choose a random IV. And as a result, they ended up with something that could have been attacked. Maybe never was. Maybe no one ever noticed it. I don't know. So like the takeaway is you have to exercise a lot of care to make sure that IVs are never reused. And like crypto is hard when it comes time to implement it. There's all these details that can like bite you in the butt, and you make this minor little mistake. And the really nasty thing is you make this minor little mistake, and from a functionality perspective, everything seems to be working fine. So you don't even notice that you're insecure. It's not that the thing crashed or someone's getting garbled exams. If that happened, then they would complain and you would figure out the bug and you'd fix it. But no, you had no way to notice that this bad thing was happening. It was just silently insecure. Okay, so to prevent IV reuse, one very common way to make sure that we're not reusing IVs is to choose every IV or every nonce randomly. And then the chances that you reuse one is very low. It's a very simple engineering solution. Okay, so how do you choose between those two? Either are fine. Either are fine. The differences between them are minor. They're in the details. They're both secure. They're both efficient. Have a little bit, counter mode has a little bit better efficiency if you can parallelize. It's a little bit simpler. If you're worried about fragility in case of an IV getting reused, CBC mode's a little bit more graceful degradation. These are minor differences. Basically, two different modes of encryption that are both fine. And there are others as well. There are others as well that are also fine. And basically, they're all fine with very minor differences in like engineering trade-offs. So for instance, if you wanted to play around with one for yourself, you could go look up CFB mode encryption, which is another way that's kind of like in between counter mode and CBC mode. And you could think about how to convince yourself whether it's secure or not and whether it can be parallelized. All right. One shortcoming of all of these modes of operations is that they only provide confidentiality and they don't provide any integrity or authenticity. If an attacker modifies the ciphertext while it's in transit, these are not designed to detect it. There's no guarantee it'll be detected. If we look at counter mode, if a message is encrypted with counter mode, Alice encrypts the message and sends the ciphertext, but Mallory modifies the ciphertext while it's in transit so that what Bob receives is different from what Alice sent. Let's say Alice sent the message, pay Mal $100. Let's look at that 100. Let's suppose that Mallory wants to tamper with this message. I claim Mallory can tamper with the ciphertext so that when it's decrypted, what Bob receives is a message that says, pay Mal $900. Let me show you how that could happen. Just look at this byte position that corresponds to the encryption of the 1 in the $100. 1 in ASCII is hex 31, and that gets XORed with some pad to get a ciphertext. What is the hex for 9, the digit 9? 39. 39. What bits would you need to flip to change 31 to 39? How many bits? 1 bit. Not the least significant bit. Not the bit in the 1's position or the 2's or the 4th, but the 8th position. So that's like the 4th bit up, starting from least significant. Okay, so if you could, so let's look at what happens if Mallory flips that bit position in the ciphertext. Flipping that bit changes a 5-8 to a 5-0. So suppose that Mallory changes the ciphertext from 5-8 to 5-0 by flipping that 1 bit in the ciphertext. What happens when that gets decrypted is the 5-0 gets XORed with the pad. It's almost correct, except the bit that corresponds to the 8 position has been corrupted, has been flipped. When it gets decrypted, it's decrypted almost correctly. Each bit position is decrypted independently. So all the other bit positions decrypt correctly, but that 1 bit position for the 8 position gets flipped. So if instead of decrypting as 3-1, it decrypts as 3-9, which is the ASCII for the ASCII digit. So Mallory, if Mallory can convince Alice to pay $100 for something, Mallory sells her bicycle for $100, and Alice sends to the bank, pay Mallory $100. If Mallory can tamper with that ciphertext while it's in transit to the bank in this way, then the message the bank actually receives is pay Mallory $900. And so Mallory receives $900, even though Alice only intended $100. So encrypt does nothing against this threat. It does not provide any integrity or. So I'm going to stop right here, and next lecture we'll see how to solve the problem of integrity and authenticity. We need a separate tool for that. I'll see you next week.